Hello everyone, my name is Chaitanya and today I'll be discussing our paper on leveraging state-of-the-art ASR techniques for audio captioning. To give a quick introduction about automated audio captioning, it's a task where we generate natural language descriptions or captions for a given audio signal as shown here in this example, like a church bell is tolling 4 times in a church center. And the intuition that we are going to use in our paper is that like this task is a sequence to sequence modeling task and is uh, similar to an automatic speech recognition task or the ASR task, but the difference is that like here we are focusing on captions instead of audio transcriptions. The popular models like for this task are based on like CNN and transformer encoder decoders, and the data sets that are popular for this task are Clotho and AudioCaps. One of the challenges in this task is that there's limited availability of captioned audio. So we would require like some sort of pre-training or other external data to make this task like perform better. The contributions of our paper are as follows. Like we first of all leveraged end-to-end state-of-the-art ASR techniques involving a conformer-based model for this captioning task. And we introduced like pre-trained audio neural networks called PANs, and we extracted audio tags and embeddings from the audio signals and used them as auxiliary features to our model. And we also performed a shallow fusion using a pre-trained RNN-based language model. And finally, like we showed that this model has like significant performance improvement over the baseline model. This is an expansion of our DCASE 2021 challenge report, and like and here we provide like more details on the methodologies and the key insights that we gained from this from our analysis and like the ablation studies for the PANS features and the shallow fusion. And finally, like for reproducibility and like easy accessibility, we have released our captioning system on GitHub. The proposed methodology is as follows, like a brief is as follows. So basically like we have an audio signal. Here is the church clock and like we have its log mel filter bank features. And we are going to use like spec-aug based data augmentation and input that as the input and use that as an input for the conformer and transformer based encoder decoder system. And parallelly, we are also going to input the audio signal to the wavegram log mel CNN14 model or a pre-trained PANS model to extract like the 527 tags. The tags are like for different categories like speech, bell, and so on. And we also have a 2048 dimension embedding vector that we are going to integrate with our encoder output and then like use it with the and use it for decoding. And finally, like the transformer decoder and the pre-trained RNN language model are fused using shallow fusion to obtain the final caption. Now, just to look at the encoder-decoder framework, the encoder consists of a convolution subsampling layer and like several conformer blocks. Like each conformer block has a feed-forward module and a multi-headed self-attention module and a second feed-forward module in that sequence. And the transformer decoder is basically has like several transformer blocks, and each of these blocks has a multi-headed self-attention module and a linear layer sandwiched between two normalization layers. The pre-trained PANS model is as I mentioned before, like it's a wavegram logmel CNN14 model, which basically has like 14 convolutional layers, and it outputs a softmax vector for each of the uh, each of the tags that is shown here like as an example, and also a 2048 dimension embedding vector that we obtained from the last CNN layer. And these both features are concatenated into a single vector and projected linearly to the same size as the output of the conformer encoder, and like they are added here before sending to the transformer decoder. And finally, like the outputs of the transformer decoder and the RNN language model are fused using shallow fusion. So this integration is done using inference by combining the scores, the attention scores for the hypothesis H, and the look ahead word token scores from the language model. And we are going to like combine them using a scaling factor of gamma. We performed our experiments by downsampling the uh, Clotho dataset from 44 kilohertz to 16 kilohertz, and we trained on the audio caps and the Clotho dataset. And we performed like spec augmentation and compared it with the DCASE task 6 challenge baseline system. And the shallow fusion was done with a scaling parameter of 0.2. Our results showed that uh, on both the development validation and the development evaluation split, our models are, our conformer models are performing like much better than the baseline model, especially if we look at the final spider score here. So the baseline model is only able to give a spider score of 0.05 versus our model ensemble is able to perform much better at like 0.224. And we also to get like a better ensemble, we had like different variations of our model, like smaller encoder decoders or smaller attention, larger kernel size, and using the auxiliary features, which is the pans model outputs. And we also included our analysis for uh, our analysis with additional training data, which is the development evaluation split, and correspondingly the similar things for the development validation split here. And we also performed ablation studies for our pans, tags, and embeddings models. Uh, sorry, pans, tags, and embeddings input. So when we have like both of these tags and embeddings, we achieve a spider score of 0.215 for the validation split and 227 for the evaluation split. And when we remove the tags, the performance drops, and like when we remove the embeddings, also the performance drops. So this shows the significance of our tags and embeddings towards the overall performance of our model. And similarly, like when we remove the shallow fusion using the RNN language model, the performance again like drops to 0.199 for the development validation set, and uh, here like little less to 0.225 for the evaluation set. We conclude that like we can leverage ASR techniques for automated audio captioning tasks. And here we propose several variations of our conformer model. And we demonstrated a significant performance improvement over the baseline model. And we also performed ablation studies to fully understand the impact of our PAN's auxiliary features and the RNN language models like shallow fusion. This process of like using ASR techniques for audio captioning actually opens up like new research directions towards joint modeling of ASR and ASC, especially for speech signals that are spoken in like noisy environments with some background noise. Thank you so much, and I would appreciate like if you have any questions.